He's a hype factory.
How I take notes.
Yeah, hit record.
Woo! Is this all necessary?
Hey, I know there's something in your hair.
Color coded?
No, you know, it's like a...
Oh, now you just, yeah.
Yeah, I definitely didn't do that.
No.
Jesus.
Alright. So let's go ahead here and take a look at the board immediately. Here's how today is going to go. Okay, first of all, here at the beginning of the period, we're going to be finishing up Chapter 4 with a problem that kind of nicely combines together a bunch of the stuff that we saw last time we saw this. And then before we get to Chapter 5, which is just a continuation of dynamics, where we now begin to look at other situations involving forces, we're going to pause and take a look at the Mechanical Universe episode for dynamics, and that is the episode specifically on inertia. It's going to go through exactly what it is that Galileo did in terms of his experiments, but perhaps a little bit more importantly, it also goes through the history of exactly what happened to Galileo at this period of time in the early 17th century. Unfortunately, today we are still dealing with the consequences, even 400 years later, as to what it was that exactly happened to Galileo. We'll see that then in the middle of the period. And then after that, we'll start to take a look at Chapter 5. And once again, it's just a continuation of Chapter 4. We'll start to examine specifically forces of friction. This is one of the things that we ignored in Chapter 5. But before we get to that, let's go ahead and finish up Chapter 4 with the following example, which nicely combines together a lot of different things. Now, there is a detailed drawing that goes along with this problem, of course. I'll draw that out for us in just a few minutes. Okay, now this double incline problem, if you will, is drawn out in the following way. Let's say that we have a steep incline here on the left and a shallower one like so on the right. And then what we're given is that the shallower angle here, call it theta, is 30 degrees. And then the steeper one here on the left-hand side, let's call it phi. This angle here is 60 degrees. Okay, and then we have our two objects here. We first of all have an object like so. Secondly, like so. Well, once again, it says in the problem that both of the inclines here are frictionless. Okay, now combining together an incline problem, like the very important example, by the way, that we saw at the end of class last time, with other examples that we saw last time with pulleys and so on, what we have here is a frictionless pulley like so, and then the two objects are connected by a string. Let's say here and here, like so. Now the two strings there, or the two sides of the string, I guess I should say, those are both parallel to their respective slopes. It wouldn't be anything other than that in introductory problems. Okay, now the easiest way to picture this problem is to imagine the object's initially at rest and then we just kind of let it go. Notice that it's not intuitively obvious what the direction of the acceleration is going to be for the following reason. We're given the mass of this object here on the steeper slope, call that M1. 1 kilogram. But this guy over here, notice, is more massive. This guy on the shallower slope we'll call M2. That's given to us as 1.5 kilograms. So even though this one here is more massive than this one, this is at a shallower angle of inclination than this, so it's not immediately obvious which way the direction of the acceleration is going to be. So because of that, all that you simply do is just assume a direction for the acceleration, set up F equals ma for each object, and calculate the acceleration. If you end up with a positive number, then you guessed the direction of acceleration correctly. If you end up with a negative number, it's just simply in the opposite direction. If you end up with 0, that just simply means that the objects remain in constant velocity. So it's not intuitively obvious in this problem what the direction of the acceleration is, so I'm just going to make a guess. I'm going to assume that the object accelerates like this. And then when I eventually set up my equations, if I get a positive number for the acceleration, I guessed correctly. If it's negative, it's just in the opposite direction, and so on. So you just pick a direction and just kind of go from there. Now, because we saw an incline at the very end of class last time that was kind of on this side of the diagram, let me actually start my force diagrams here by taking a look at M2 first. Okay, so for object M2, we first of all have the normal force. It's perpendicular to the incline. Let's call that N2, like so. And then we have the force of gravity downwards, the object's weight, M2G. But then we also have the string there in red. We have a tension vector like so that is up the slope. Now, depending upon how neat your own force diagram is, you may want to indicate that this right here is a right angle, like so. Okay, now I'm assuming that the direction of the acceleration, remember, is up the slope like so. So now here's then what I have to do. I don't have to resolve tension into components because it's already parallel to A, nor do I have to do this with a normal force because it's perpendicular to A. Instead, however, I have here the object's weight, M2G, on an angle with respect to A, so we do have to break this into components. We break this into components exactly the same way as you saw me do the problem at the end of the class last time. We break M2G into a perpendicular component like so, and a parallel component here. The reason why we do it this way, as opposed to, say, doing it like this, is because, as you saw from the geometry last time in class, this angle right here is the same as the angle of inclination. This right here is the angle of theta. There's a very easy way to remember this, by the way. You just simply come down from the normal force and go across like so, thereby forming these red components in this manner and showing the angle of theta. Okay, now I have to add stuff up using F equals ma. Okay, first of all, in this perpendicular direction, there is no acceleration, so everything cancels. The normal force here, N2, does not quite cancel out with M2G. Instead, it cancels out with this adjacent component right here of M2G. This adjacent component right here, if you remember from last time in class, is equal to the hypotenuse of this little right triangle, M2G, multiplied by the cosine of the angle theta. So N2 cancels out with M2G cosine theta. So. And now, using F equals ma, we add everything up in the parallel direction. It is parallel to the slope like so. Now, I'm assuming that A is up the slope, so that's my positive direction, if you remember one of the basic rules for adding up force vectors last time. The tension vector here points in the same direction as A, so I think of this as a positive number, but then this component here of M2G, the opposite side of this triangle, this guy right here points down the slope in the opposite direction of A, so I have to think of this as negative. This quantity right here, by the way, remember being the opposite side on this little right triangle, is equal to the hypotenuse multiplied by the sine of the angle theta. So this guy right here is M2G sine theta. So when I add stuff up now in this parallel direction, I'll have first of all positive t, and then minus M2G sine theta in the opposite direction equals then M2a, like so. And then like we saw with pulley problems and so on last time in class, with this first expression here, we have two unknowns. One of the unknowns is the force that occurs between the objects, which once again we usually don't care about, and the acceleration of that I'm trying to find. So now we take a look at the forces acting on the other object, M1. Don't be fooled by the fact that it's on the other side of the diagram. It's virtually going to be the exact same force diagram as M2. It's just left-right has been reversed. Other than that, it's essentially the same thing. But drawing it out carefully, M1 now, the forces acting on it will be as follows. Okay, first of all, we have the normal force that's perpendicular to the incline itself. So that's N1 that looks like this. Okay, then tension up the slope like so. That looks like this. And once again, depending upon how neat your own diagram is, you may want to indicate that this right here is a right angle. And then, of course, we have the force of gravity, straight downwards, M1G, like so. So it's basically the same force diagram as the one on the other side, it's just that left and right have been reversed. Okay, now we're assuming that the direction of the acceleration, remember, M1 is down the slope, like so. So I don't have to break the normal force up into components because this is perpendicular to A. I don't have to break the tension up into components either because that's parallel to A. However, M1G is on an angle with respect to A, so yeah, we do have to break that up into components. We break it up into components exactly the same way as I did on the other side of the diagram. Once again, the easiest way to remember this is come down from the normal force and go across like so. That's the easiest way to remember it, thereby forming right here the angle in this case, which is the angle phi. Okay, now we add everything up again, once again by using F equals ma. First of all, in this perpendicular direction, everything cancels out. So the normal force N1 cancels out with our adjacent component here of M1G. This is M1G cosine phi. Like so. And now in this parallel direction, in this case, notice that it's going to be the M1G sine phi, that's the positive, and the tension will be negative. The reason for that is because remember that our direction of acceleration, which defines for us the positive direction, is assumed to be down the slope. So right here pointing in the same direction is a positive M1G sine phi, and then subtract the tension in the opposite direction. So M1G sine phi minus the tension T equals then the net force acting on object M1, and that is of course M1A. So there is then the second of my two equations, two unknowns, and then we just run through the remainder of the algebra here to ultimately find what the acceleration is. So doing the algebra, you've got to be a little bit careful as you go. What we'll do is jump back up to the top here and solve for tension. So I'll move that term to the other side, like so. And then take that expression for the tension and plug it into here, and when we do, we have to subtract both terms. So just be careful about distributing your negative sign in that manner. So I now have M1G sine phi, and then minus T, so minus both of those terms. Like so, equals then the right-hand side of the expression, M1A. And now at this point, I only have one unknown, and that is the acceleration A, which we can now pretty easily solve for. So the next step is to move this term here to the other side, and as I do, I'll go ahead and factor out the A from both terms. So you could do a couple of these minor steps at once you get a little bit of practice. So. And then the last step here, of course, is just to divide by the parentheses on both sides to get the acceleration by itself. And when you do, you end up with a formula here for the acceleration that looks pretty similar to the acceleration formulas that we saw last time in class for the various pulley situations that we looked at. You always end up with, in these situations, some combination of weight in the numerator divided by the total mass in the denominator. And now before I actually plug the numbers in, and we eventually do in fact get our answer, notice that numerically, in that equation, specifically the numerator, there are three physical possibilities. Before I do, repeat your question.
Why is M2A and not, why is it negative?
Okay, so we've got, first of all here in blue, M1G sine phi minus T equals M1A. Now up above, what I did algebraically here with the red equation is I solved for T and obtained this. And then I take this expression for the tension and I plug it into there. When I do, however, I have to make sure I take the negative sign and distribute it through both terms like so. And then I just move this guy to the other side, beginning the process for solving for the acceleration. Okay? So a very easy mistake to make, by the way, is to don't forget to distribute the negative sign through both terms when you do your algebra. Okay, now as I was saying over here on the right-hand side, specifically with the numerator, this tells us the possibilities that could occur. Because for example, This number here could be bigger than this number, meaning that the acceleration is positive and it accelerates exactly as I guessed. It is possible, however, if the numbers work out just right, for these two terms to cancel out. And if they canceled out, the acceleration would be 0 and the objects would remain at constant velocity, whatever their initial velocity was. And then the last possibility is that this number here could be in fact be bigger than this one, meaning the acceleration would be a negative number. If the acceleration is negative, it doesn't necessarily mean that the objects are slowing down. All that it means is that the direction of the acceleration is in the opposite direction of what I assumed. So now after all that, let's finally see what happens. I'm mildly curious. So I first of all have here, remember that M1 was on the left-hand side of my diagram, that was 1. So 1 times 9.8 times sine of 60. 9.8 times sine of 60. Okay, and then minus 1.5 times 9.8 times sine of 30. So minus 1.5 times 9.8 times the sine of 30. And then divided by the total mass here, which is actually a total of 2.5 kilograms. I actually do, in fact, get a positive number here. It's pretty small, though. It's a little bit less than 1/2 of a meter per second squared. But being positive, that means that, yes, I did, in fact, correctly guess the direction of the acceleration. The object's acceleration is in the direction that I am. So the objects accelerate in the direction of the Yes, sir.
So if you get 0, which way does it accelerate?
Okay, so if I end up with an acceleration of 0, that then means that the objects would be at a constant velocity. So if they were at rest, they would stay at rest. If they were initially moving like this, they would continue to do so at constant velocity. If they were initially moving like this, they would continue to do so at constant velocity. So notice in this problem that the initial velocity of the objects is not given. That's not important, however, when calculating the acceleration. It would become important if we were asked to do some sort of kinematics afterwards, okay? Yes?
So if our initial dot was negative 0.45, then our acceleration would be the opposite.
Opposite direction of what we had guessed.
So it would still be 0.45.
In magnitude, yes, it would be
Okay.
0.45 meters per second squared in magnitude, just in the opposite direction. Now, if you do a problem such as this on WebAssign, they will be explicit about the direction. It'll say, okay, find the acceleration, blah, 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 and then indicate its direction, like left or right or something like that. They'll be explicit about it. Okay? Okay, any remaining questions? Very good. Okay, that completes for us now chapter 4. Let's kind of switch gears. This first. Switch some of this. I want to start just, yeah, I want to introduce you first. Pass out to you the Cornell Notes template. As always, you are to take Cornell style notes. I will collect this at the beginning of the very next time. I'm sorry? The next exam is actually not going to be until after we cover chapters 4, 5, and 6. It won't be until just before Thanksgiving break. So we don't have
So much easier.
we don't have, I don't do quote midterms, I just do unit tests.
We have finals.
Yes, there is a final.
Oh,
Yes, there is a final second semester as well. Okay, relax.
There's a second semester final like you will.
But then what happens when we cross the international date?
That is complex.
Your first semester final is contiguous. All right, now, let me preface for you the film in the following way. As you know, Galileo firmly supported the idea of Copernicus. The sun is the center of the solar system, all the planets, including the Earth, orbit the sun, blah, blah, blah. However, Galileo knew full well that what he was supporting was, in the eyes of the Catholic Church, heresy. Galileo was Italian. He lived in Italy. He lived in the heart of Roman Catholicism. Because of his views, he came into direct conflict, of course, with the teachings of the Catholic Church, and it led him, unfortunately, into a large amount of trouble. The trouble that Galileo faced in this context, unfortunately, even 400 years later, we are still dealing with it to some extent. So it is important, and not just as physics students, but as people that are being educated, that you know exactly what it was that happened at this period of time, okay? All right, let me go ahead and get this started. There is, by the way, a great joke at the end of this film. Watch for it carefully.
Is it a physics joke?
28 minutes or so.
What's the date?
Can you guys still see enough if I close the door to here?
Yes.
This program was provided by the Annenberg CPV project.
Any object moves with constant speed in a straight line, unless it's acted upon by an outside agent. That fundamental principle is called the law of inertia.
Today I'd like to tell you a little bit about Galileo. Why is it that we always call Italians of a certain period by their first names as if they were good friends of ours? Not only Galileo, Dante, and Leonardo, and Raphael. It's strange. In any case, today I would like to tell you about our good friend Galileo Galilei. Here is a picture of Galileo made from a woodcut that was made while he was still alive.
Two very important men were born in 1564. William Shakespeare in Stratford and Galileo Galilei in Pisa. As a youth, Galileo had first set out to study medicine at the University of Pisa. But he soon realized that medicine was not for him. When he found out that there was no professor of mathematics at the university, he dropped out of medical school. He taught himself mathematics, wrote a few papers, and began to build a scholarly reputation. And in the year 1589, with the help of a well-connected friend, he was appointed professor of mathematics. At the time, the university was dominated by Aristotelian scholars who saw little value in mathematics. Galileo considered his Aristotelian colleagues to be fools, and immediately got into trouble by baiting and ridiculing them. It soon became obvious that when his 3-year contract was up in 1592, he wouldn't be reappointed. So, when a position was offered to him at the University of Padua, he accepted it without hesitation. At Padua, he lectured in Euclidean geometry, Ptolemaic astronomy, and Aristotelian mechanics. He conducted his noted research on falling bodies and inclined planes.
Those are some of his original pieces. They survive to this day. I've seen them.
And in the year 1610, Galileo pulled off perhaps the greatest academic sleight of hand of all time. A Dutch lensgrinder named Hans Lippershey had discovered a remarkable new device, the telescope. As soon as Galileo heard about it, he figured out how it must work. came up with his own design, and built a telescope of his own that magnified images by about 9 times. Then he called together the city fathers of Venice for a demonstration in the famous tower in St. Mark's Square. He told them, "Look at the horizon through this device. With it, a ship approaching the city can be seen 2 hours earlier than it could with the naked eye. For a maritime power like Venice, this device is absolutely essential." Galileo didn't claim that he invented the telescope, but he also didn't bother to point out that he hadn't. The city fathers were so impressed that they gave Galileo a lifetime position at a handsome salary. And within 2 months, models of Galileo's telescope were being sold by vendors on the streets of Venice as children's toys. Galileo had made himself financially secure for life by selling the city fathers a child's toy. But Galileo had much more important things in mind for the telescope. He built a number of larger, more powerful telescopes, including one that would magnify images about 30 times. Today, 2 of them are on display in the Museum of the History of Science in Florence.
I've seen them.
With these telescopes, Galileo looked at the sky and made some remarkable discoveries. The moons of Jupiter, which even today are called the Galilean satellites. Mountains on the moon. The phases of Venus. And spots on the face of the sun. Even now that we've walked on the surface of the moon, Galileo's sketches reveal that his views were amazingly accurate. In time, Galileo's astronomical discoveries, along with the ideas of Copernicus, would intellectually shatter the serenity of the heavens. To anyone who dared to look through Galileo's telescope, what they saw was the beginning of the end, with the world views of Aristotle and Ptolemy, and the beginning of a great deal of trouble for Galileo Galilei. By the early 17th century, Europe had seen the Renaissance, the Protestant Reformation, and the Catholic Counter-Reformation. Sweeping changes had shaken every part of the medieval system. Religion, art, literature, music, mathematics, and the sciences, especially astronomy. Before the Renaissance, Aristotelian mechanics and Ptolemy's design of the heavenly spheres were the order of the day.
Earth at the center of the universe.
They were the logical, accepted, and unchallenged natural order of the universe. And so it was until a Polish monk looked upward and saw things differently.
Copernicus.
In opposition to the Ptolemaic view, Copernicus saw the Earth as just another planet circling the larger, grander sun. Within the Catholic Church, some saw the Copernican system as a threat. It seemed, like the Protestant heresy itself, to challenge the absolute authority of the Vatican. Nonetheless, it took the Church 75 years to make her displeasure fully known. And in the interim, the Church had to contend with a problem much closer to home than the sun. Catholics and Protestants were locked in a war for the very soul of Europe. Copernicus, like Martin Luther, challenged the Church's interpretation of Holy Scripture. But the Copernican system also seemed to defy elementary common sense. Heavy objects naturally fell toward the center of the Earth, because that was the center of the universe.
According to the Greeks.
If the Earth really is spinning and hurtling through space, why doesn't everything fly off? And if the Earth really is spinning, why should an object dropped from a tower land directly below?
This is what the Greeks thought would happen.
Why doesn't it land in the next city-state, or at least some distance away? 300 years ago, those were logical, intelligent questions. And Galileo Galilei set out to find the answers. Galileo was, despite his independent nature, a very popular figure, generally respected and admired. And to the Church, his God-given intelligence made him a favorite son. No doubt Galileo enjoyed the attention. His hunger for fame was enormous. But his thirst for knowledge and for the truth was even greater. Early in his career, while a professor at Padua, Galileo did quite well for himself as an academic entrepreneur. Among other things, he tutored royal princelings in subjects such as magnetism and mathematics. But in the long run, his use of the telescope was much more important. His first book, The Starry Messenger, revealed his remarkable observations. The publication of The Starry Messenger elevated Galileo to a position of renown throughout Europe. Yet in certain circles, his discoveries were not altogether welcome. Through his telescope, Galileo had seen something unimagined, or at least unspoken, by the followers of Ptolemy. The moons of Jupiter seemed to prove that the Earth wasn't the center of all motion in the heavens. Did he have within his sights the proof that Copernicus had been correct? Contrary to both Aristotle and the doctrine of the Church, was the Earth merely another planet orbiting around the sun? If that were true, the question remained, why in the world doesn't everything spin off? Aristotle's ancient view was that all things, by their nature, have rightful homes to which they want to return. His ideas of absolute rest and absolute motion seem confirmed by common sense. And based on the common experiences of everyday life, how could anyone take the idea of the Earth's hurtling through space seriously? It was one thing for Galileo to criticize the prevailing Aristotelian point of view, but quite another to show how and why things worked within the Copernican system of planetary motion. But even before the invention of the telescope, Galileo had prepared himself to do exactly that. To lay the groundwork for his law of falling bodies, he had painstakingly observed and timed balls rolling along inclined planes. These experiments also led him to another profound idea that would come to be known as the law of inertia. Galileo realized that a ball, after rolling down one inclined plane, would roll up another until it regained its original height, no matter what the steepness of the second plane was. If the incline of the second plane was shallower, the ball would roll farther along, not stopping until it was as far above the horizontal as it had been at the start. The more nearly the second plane was horizontal, the farther the ball would roll, trying to regain its original height. Therefore, on a perfectly horizontal plane with a smooth surface, a ball would never come to rest. It would keep rolling forever. This was the crucial realization that Galileo needed to explain why everything, including his critics, could keep up with the spinning surface of the Earth. A body in horizontal motion tends to keep moving that way forever. But everything on the surface of the Earth is in horizontal motion at exactly the same speed as the surface of the Earth itself. There's not even any friction to affect the body's motion, because everything moves together. With this remarkable concept, Galileo overturned the ancient Aristotelian dogma that it's natural for all bodies to come to rest. Although Galileo's concept was brilliant, it wasn't entirely accurate. Still influenced by the Platonic ideal of circular motion, Galileo thought that a body in motion would continue forever, but only in the horizontal direction, not in a straight line, but round and round, following the surface of the earth.
Okay, so as they just described here, it turns out that when it comes to the law of inertia, yes, Galileo is credited with its discovery, and very crucially, he used it to explain how the earth can be in motion, for example, yet we don't feel its motion. But it turns out he didn't quite get it correct. He interpreted, for example, the horizontal direction to represent the surface of the earth, round and around in terms of a circle, as was described. In other words, he didn't get the straight line aspect of the law of inertia correct. That was actually figured out a little bit later on by a French mathematician named René Descartes, who we will get to at a later date. But even though Galileo is credited with the discovery of the law of inertia, he essentially got the gist of it. He just kind of missed the straight line part of it.
A generation later, René Descartes straightened everything out, giving the law of inertia its final shape. Objects in motion don't tend by themselves to come to rest. They tend to continue as they are until something interferes. That fact's easier to see now than it was in Galileo's day. Today, few would disagree that the planet Earth hurtles around the sun.
Oh, but they're out there. In
A
fact, they're
sun
in
that moves
Congress
around
right
one
now.
corner of a galaxy. A galaxy that moves alone in a cluster of galaxies, all streaking through the unimaginable vastness of the universe. How does the idea of rest fit into this grand scheme of things? It doesn't. Nothing in the universe comes to rest. Instead, anything and everything will continue to move as it is in a straight line at a constant speed until something interferes with it. That's the principle of inertia. And it's both as simple and as profound as any idea that's ever been pondered. Obviously, objects can seem to be at rest, but that's only because they're in the same state of motion as the viewer.
Same reference frame.
Whether an object is at rest or in motion depends completely on viewpoint, on whether the observer's moving right along at the same speed. Absolute rest does not exist. Absolute motion does not exist.
It's only relative motion.
Even hurtling through space at an incredible speed, relative to the moon or the sun or the center of the galaxy, the natural tendency of any object is to retain whatever motion it has. In Galileo's day, that was a very difficult concept to accept. To an Aristotelian, the motion of a cart required and had a logical explanation. Unless something came along to push or pull it, it wouldn't move. Therefore, its natural state was that of rest. But to the modern observer, a vehicle in motion needs no explanation. This coasting object will keep moving until the brakes, or something else, brings it to a state of rest. But what about an object that's not just moving horizontally along with the surface of the earth? What about a projectile launched into the air? Or a ball dropped from a tower?
Once again, this is according to the Greeks.
Shouldn't the spinning earth leave the falling ball behind? Galileo said it shouldn't. He said the ball should continue to move horizontally with the earth, even as it falls vertically toward its surface.
And then, of course, this is what really happens.
In the Renaissance, this concept was as hard to grasp as quicksilver. So Galileo offered his contemporaries an analogy. He asked people to picture a ball falling from the mast of a moving ship. To a sailor on the deck, the mast is standing still. He wouldn't be surprised to see the ball fall straight down onto the deck at the foot of the mast. on shore would see the ship and, of course, the mast in motion. An Aristotelian observer would have no doubt at all about what should happen. The ball should fall directly toward the center of the earth, while the ship sails out from under it.
Okay, once again, this is according to the Greeks.
A sailor on deck would see the ball hurtle toward the rear of the ship rather than fall to the foot of the mast. Though the experiment was probably never performed during Galileo's life, the results are precisely what he predicted. The ball falls straight down along the mast. The ball falls along the mast because both objects, ball and sailboat, share the same initial motion. If they don't share the same initial motion, then the result is just as the Aristotelians would have expected. But when dropped from the moving mast, the ball falls vertically while moving horizontally with the boat. Together, these motions form a curved path, a parabola. Galileo realized that these same principles would cause the motion of any projectile to follow a parabolic curve, whether at sea or on land. A ball dropped anywhere on the surface of the spinning earth behaves the same. Here, sharing the horizontal motion of the planet, it falls straight downward and lands at the base of the tower. In these terms, Galileo saw and proved something new under the sun.
Okay, now pay close attention to the history.
In 1616, Galileo was summoned to Rome. He was told to neither hold nor defend this idea of the earth moving around a stationary sun. Knowing that the Church officially objected to the Copernican system, he waited for the right moment to convince them of the error of their Aristotelian ways. In 1623, Galileo thought that the moment had arrived. His friend and protector, the brilliant Cardinal Maffeo Barberini, became Pope Urban VIII. To enhance his case, Galileo wrote a book, a dialogue in which characters debated the Aristotelian and Copernican systems. As an author, Galileo was a clever politician. The Aristotelian character argued skillfully and was declared the winner, a ploy which was to be Galileo's defense against teaching the Copernican view. However, as any reader could easily gather, the Copernican arguments were much more solid. And perhaps worst of all, since those arguments were in fact written in Italian rather than Latin, common Italians could readily understand them. And as far as the Church was concerned, Galileo made a few more errors of judgment. His fictional defender of Aristotle, who spouted the same arguments the Pope had been making, happened to be named Simplicio, the simpleton. And perhaps most damning of all, Galileo's new book challenged the Church at the very time when it was being challenged from all sides. Galileo was put on trial in 1634. His fame and prestige made it unthinkable to go further than the mere threat of torture. But to Galileo, who knew very well how machines worked, that was enough. He publicly recanted the Copernican system of planetary motion. Ironically, in the future, no serious scientist would deny Galileo's evidence. The principle of inertia, conceived by Galileo and refined by Descartes, became Isaac Newton's first law of mechanics. As far as the Church was concerned, Galileo's name would eventually be vindicated. it would take a very long time. As recently as 1983, the Galileo controversy was still unresolved. In that year, Pope John Paul II asked that the dispute between Galileo and the Church finally be put to rest.
Gee, thanks.
He said, "We cast our minds back to an age when there had developed between science and faith grave incomprehension, the result of misunderstandings or errors, which only humble and patient re-examination succeeded in gradually dispelling. The Church herself learns by experience and reflection, and she now understands better the meaning that must be given to freedom of research." But at the time, even for a famous scientist with an unpardonable ego, public humiliation was not considered punishment enough. Found guilty, in spite of his famous retraction, Galileo spent the remaining 8 years of his life under house arrest at his estate near Florence. According to legend, as Galileo headed into the exile of house arrest, he said, "Eppure si muove." Nonetheless, the earth moves.
Galileo made his real reputation by means of his great discoveries with the telescope. Before that, he had been known only to a handful of experts, but afterwards, he was famous throughout Europe. As a faithful son of the Church, he knew it was making a terrible mistake in turning its back on Copernicus. But the Church, under pressure from the Reformation, hardened its position on the literal interpretation of the Scriptures. Galileo was naive and arrogant, and he thought he could make the Church change its mind by means of logical, scientific arguments.
Good luck.
That might have worked earlier when the Church was more intellectually flexible, but in the 17th century, it was hopeless. Furthermore, Galileo did something that was even worse. Instead of writing his book in Latin, which only a handful of scholars would have understood, he wrote it in Italian, which anybody could understand. That was a challenge the Church couldn't ignore. And so, in 1634, he was put on trial. And in spite of recanting publicly his Copernican views, he was made to spend the last 8 years of his life under house arrest at his estate at Arcetri, near Florence. When he died, his body was buried in a cathedral, and it's still there, in the Church of the Holy Cross in Florence. That is, most of his body was buried there. I like to think that Galileo was defiant to the very end, and one of his fingers can be found on display in the Museum of the History of Science. I'll see you next time.
Was that the joke? Middle finger?
Take a guess at which finger it was. Exact finger. It meant the same thing 400 years ago that it means today. Let's take a short break. I've seen the finger, by the way.
Oh, wait a minute.
Watch out, here come the lights, watch out.
There's no way to figure it out. What? Here. Soccer. No, what? It's even worse.
I'm sorry? No, it was actually done after he had died by his students, and put it on display in this manner, where it has remained to this day. Yes, that was done on purpose.
Does it still have some?
Girls, I'm sorry, I need to stand up.
I have a particular really? You're like still like muscle.
No, it's just almost fossilized bones, 400 years ago, you gotta remember. As I said, I've seen the finger.
How? But wouldn't it be like totally gone?
Did you replace the bulb?
I'm sorry?
Did you replace the bulb?
Yes, they replaced the bulb the other day. All right, let's take our short break here, that's all. I'm gonna show you.
Yeah.
And I was like go for something. Got there like 6:50.
I hate writing this
So there's
in.
6:50.
It's fine. What year was it?
Like right off the jetty.
Get him just Josh's copy, everything you do.
It was awesome.
Okay.
We have waited.
Oh.
Waiting in hell.
No, I help you with that request. We have no one.
During breaks, my class is like screaming. Like it's really crazy.
We're just too tired.
Oh,
Next time we
entire
have nap
classroom is full. You guys, they shoved 2 kids in that desk in the corner.
2 kids in the way.
Oh, you're signing. Oh.
What period do you
You're signing. Second.
What are they
Like
seniors?
nap,
Yeah,
like
there's no one. There's a few juniors. There's mostly seniors.
Mr. Shalek, what's your definition of a chipmunk?
You'll know by the end.
Alright.
What is that mean?
Mr. Shalek, that's chipmunk.
Okay, come on, it's time for box.
You have a pet chipmunk?
No.
All right, so as always, I will collect from you next time at the beginning of class the Cornell notes. Go ahead and put them aside, please. Please take out your notes. Okay, so we now move directly into chapter 5 here, where we begin to examine something that we more or less neglected for the most part back in chapter 4, and that was friction. Now, chapter 5 is still within dynamics here. It's just a continuation of chapter 4, where we now start to examine more complicated situations involving forces. So we begin by taking a look at the forces of friction. Okay, we recognize with regards to friction that there are 2 distinct types. Okay, I'll demonstrate both for you shortly in just a few moments. But for now, the first type of friction is what's called kinetic friction. Kinetic friction occurs between 2 surfaces that are moving relative to each other. Okay, but then secondly, and yes, distinctly, we also have what is called the force of static friction. Okay, static friction occurs between 2 surfaces that are not moving relative to each other. I'll give you a moment to comment on this description here. Why is it that the 2 forces here do in fact have to be a little bit different from one another? Well, it's actually very easy to demonstrate. Well, let's demonstrate it in the context of an incline. Now, of course, last time in class, at the end of the period, we went through the frictionless incline problem. And in the frictionless incline problem, there is only one possibility, and that's the acceleration of the object is going to be g sine theta down the slope. That was Galileo's free fall experiment. But when you add the forces of friction now into the situation, then the situation physically becomes a lot more complicated. A lot more things, for example, can happen. Let's say, for example, that I make the angle of inclination here quite shallow, like so, and then I set the eraser here into motion. Notice that in this case, it actually slows down, like so, due to kinetic friction. So as it's slowing down, its acceleration is definitely not down the slope at g sine theta. In this case, the acceleration is actually up the slope. So while it's moving, then, you have the following forces acting in this manner. You have mg sine theta down the slope, and the force of kinetic friction opposing the motion, thereby giving us the acceleration, as we saw, up the slope in this direction. But now notice that the eraser is not moving. Right now it's at rest, and then therefore static friction is acting on it now. If the acceleration is equal to 0 here, the mg sine theta down the slope is being exactly canceled out now by the force of static friction up the slope. Whatever that number happens to be, the force of static friction in this case, it distinctly has to be a different number than the force of kinetic friction in this situation, because while the eraser is moving, it does have an acceleration. So the two types of friction here have to be slightly different numbers. That's why we begin to distinguish between the two. Okay, now understanding where friction ultimately comes from is actually pretty simple and straightforward. Let's describe it in the following way. Let me begin by saying that let's assume that we have two finely polished surfaces. So like smooth metal, it feels very smooth to the touch. Well, it may feel smooth to the touch, but if you could say, look at those surfaces with a powerful microscope, like an electron microscope or something like that, then those surfaces are actually anything but smooth. They kind of look something like this. So we have two finely polished surfaces. They feel very smooth to the touch. And now we take a look at them at the microscopic level. So those surfaces are actually anything but smooth. They have all these little bumps and jags and whatnot associated with the surface at the microscopic level. And then let's say here's a second surface like so, in contact with the first, this, and let's say the two surfaces are moving relative to each other. So then therefore, all those bumps and jags and whatnot, they just exert mechanical forces on one another. They just bump up against each other. And this is, of course, then what we see as kinetic friction, for example, as the two surfaces move against each other. So these bumps, etc., exert mechanical forces. They bump up against each other, giving rise to friction. However, let's say that I had two perfectly polished surfaces, literally a single sheet of atoms. And by the way, such materials today can be manufactured. So let's say that I have two materials, the two surfaces, and they're perfectly polished. They're a single sheet of atoms. You're still going to have forces of friction for the following reason. So now we kind of go all the way down, let's say, to the atomic level. And we have two perfectly polished surfaces. Each one is literally a single sheet, if you will, of atoms. So for example, here's one of those surfaces like so. These are the atoms. And let's say, secondly, another surface like so. This one we'll say is moving in this direction relative to the other. Well, in a very fundamental way, what I'm actually beginning to describe here is how matter interacts with other matter. Matter is electromagnetic in nature. Think of the circles as I've drawn there as a representation of the electron clouds associated with the individual atoms themselves. So when matter interacts with other matter, there are literally, in a fundamental way, electromagnetic forces that occur. This is, in a fundamental way, ultimately where friction comes from. It also tells us then why there's no such thing as a frictionless surface, because this interaction, as matter electromagnetically interacts with another bit of matter, is fundamental in nature. This is simply the way that it is. So, matter interacts through electromagnetism. And it does so in a fundamental way. In other words, this is the way that nature works. So then, therefore, this is ultimately where friction comes from. And this also then explains why there's no such thing as a frictionless surface. Give me a moment to write down that description. Okay, now, we understand the physics of how matter interacts with other matter very well today. It's one of the triumphs, by the way, of early 20th century physics, understanding this interaction. It is, yes, very advanced physics, but we understand it perfectly well today. However, it turns out that in practice, it's actually very difficult to go from a description at the atomic level of the atomic physics that is occurring here, and then use that to explain, for example, the motion of this eraser as it moves across the desk. The reason why in practice this is extremely difficult to do is just because, very simply, there are just too many variables. There are trillions upon trillions of atoms that make up the surface of this eraser, trillions upon trillions of atoms that make up the surface of the desk. If I was going to use the atomic physics of how the eraser's atoms are interacting with the atoms of the desk in order to compute the motion of the eraser itself, it would be impossible to do from a computational standpoint. There are just too many variables. It's kind of like a similar problem as, say, trying to predict the weather accurately more than a couple of weeks in advance. We understand the physics of the atmosphere perfectly well. We understand how air masses interact with each other. We understand how what happens, for example, as the sun dumps energy into the atmosphere, blah, blah, blah. We understand all of that very well. So if we understand the physics of the atmosphere very well, why can't we then use it to explain, for example, what the weather's going to look like more than, say, accurately at least, 10 days in advance? The reason for that is just because the system is so large. There's just too many variables. It's impossible to compute something like that accurately more than a certain time in advance. Same idea here. In principle, we could use the atomic physics of what occurs here as the eraser's atoms interact with the atoms of the desk, but computationally using that to explain the motion of the eraser itself is basically impossible to do. However, it turns out that empirically, and remember what that word means in scientific lingo, based upon data and observations, it turns out that both of the two forces of friction, kinetic friction and static friction, have a few very simple empirical properties. It turns out then that explaining the forces of friction that we see at the everyday level is actually easy to do. So let me describe for you first the empirical properties of kinetic friction, and then a little bit later on we'll get to static friction. But for now, empirical properties of kinetic friction. Some of this is very intuitive. Okay, first, force of kinetic friction acting upon an object always opposes the direction of motion. However, as I'll demonstrate for you in just a moment, not necessarily, though, the direction of acceleration. Okay, this is intuitive, and it's also obvious if you think about it. To some extent, I already described it for you in a problem that I did at the very beginning of Chapter 4 involving a hockey puck, if you remember sliding across some horizontal lines. Remember what that situation looked like? Take the eraser, it moves to the right-hand side relative to you guys. And then opposing the motion of the eraser to the right-hand side would have to be the force of kinetic friction acting to the left-hand side. So the force of kinetic friction opposes the direction of motion. However, it is the force of kinetic friction in this example that gives us the acceleration to the left-hand side. So the force of kinetic friction always opposes the direction of motion, but not necessarily that of the acceleration. This is intuitive. Okay, then secondly, somewhat counterintuitively, force of kinetic friction is actually independent of the surface area of contact. And this is somewhat counterintuitive, but what it does say is it says that the surface area of this eraser, when it's in contact with the desk, has nothing to do with how much friction is actually acting in this situation. That is counterintuitive, but let me give you a nice example that illustrates this. Consider, say, two types of tires that are made of the exact same material. Imagine, say, bicycle tires and automobile tires. Now, which of the tires is obviously thicker? Okay, car's tires. So you would then say to yourself, okay, well then it means that because the surface area is bigger, there's going to be more friction. That's not the case. So why is it then that automobile tires are thicker than bicycle tires? Well, imagine taking a bicycle tire and mounting that onto a very heavy car, and then have that car go around a corner at a high rate of speed. What's going to happen to the bicycle tire when that happens? Yeah, it's going to get ripped up. The reason for that is because when you take a structure, such as a tire, and have it go around a corner very quickly, there is a large amount of sideways force that's exerted upon the tire. This is called shear. If the shear is large enough, it will literally rip apart the tire itself. So the reason why automobile tires are thicker than bicycle tires actually has nothing to do with the friction. It's made of the same material. Instead, it's just so the automobile tire can withstand the shear as it, say, moves around the corner. How many of you, by the way, have ever changed a tire to the spare? Okay, a couple of you have. It's a very useful skill to have, by the way. If you haven't done it already, sometime in the future, sure enough, you will. But those of you that have changed to the spare, have you ever had to change to that smaller spare that is sometimes included in some cars? Sometimes called a mini spare. It's the same height as a normal automobile tire, but it's a lot thinner. If you read the directions carefully for that mini spare, there will be a warning label on it. It will say, don't drive the car faster than 30 miles per hour or something like that while using the spare. The reason for that has nothing to do with the friction. It has to do with the shear. Because if you take that small wheel and you put it on a car and then go around a corner at a high rate of speed, then the shear is going to rip apart the tire. So that's why that warning label is there. Another nice example to consider, kind of along the same lines, is like an automobile racing. Like in IndyCar racing, it was really big, fat, thick tires. The reason why is because those tires are made of a very soft rubber. Soft rubber, when you place it in contact with concrete, generates a large amount of friction. So then therefore, why are the tires themselves so big if the surface area has nothing to do with the friction itself? The reason for that is because very soft rubber, if it's really thin and you go around a corner at 100 miles an hour, like in automobile racing, then the shear is going to rip it apart. So that's why those tires are so fat. It has nothing to do with the friction itself. It's just so it can survive the shear as it goes around the corner. So this is somewhat counterintuitive, but it is the case. And by the way, as I describe these empirical properties of kinetic friction and we begin to work with them, later on in a mini lab exercise, we'll actually verify all of these properties. It turns out to be really easy to do. Sean?
So say a bicycle tire, just maybe 2 inches wide, will have the same amount of friction as the car tire 5 inches wide?
Yeah,
Okay.
yeah, it'll have the same amount of friction. Now, as we'll see, the friction that's present actually also depends on the weight of the vehicle itself. We'll see them come out in the last property. But in terms of the material, the surface area of each tire has nothing to do with how much friction is actually generated. Okay? Yeah?
So you said that it can't withstand you said the smaller spare. So let's say we're just going straight at 60 miles an hour, would that matter?
Well, you also have to remember that with the friction with the roadbed, you're also going to generate some heat. This is what breaks down tires as well, and this is why you have to replace them now and then, because the tires themselves actually get eroded the more and more that you use them. That's just from the heat that is generated by friction. So then therefore, if you have a small tire, and you have basically the more or less the same amount of heat that's being generated, the tire is going to break down that much faster. So this is why they always warn you with that little mini spare, is to basically change back to a real tire as soon as possible and don't drive that fast.
But technically it could withstand going as fast if you're going in a straight line, just not.
Yeah, but just not for very long, because eventually you'll basically melt the tire, to put it simply, okay? Okay, thirdly, in the force of kinetic friction acting upon the eraser, for example, as it slides across the desk, doesn't depend upon the relative velocity between the surfaces. In other words, as the eraser slows down, the force of kinetic friction acting on it is actually a constant. Combined with the second property, this actually makes kinetic friction really easy to describe mathematically. But it's once again independent, that is, the force of kinetic friction is independent of the relative velocity between the surfaces. It doesn't change as the eraser slows down or speeds up, for example. And then lastly, fourth, and it's with this fourth property that we begin to quantify the force of kinetic friction. And this is also intuitive. I'll write out the phrase completely here for us. The force of kinetic friction is directly proportional to the normal force. Okay, this is actually intuitively obvious if you think about it. Think of it this way. Okay, this little eraser that I've been using here to demonstrate weighs next to nothing. In English units, it weighs a couple of ounces at the most. Okay, an ounce, by the way, is 1/16 of a pound. So as this eraser is sliding across the desk, the force of gravity downwards, mg, just a couple of ounces, is the same thing as the normal force upwards. So the normal force right now on the eraser is a small amount, therefore the force of kinetic friction is a small amount as it slides across the desk. However, what do I do to the normal force acting upwards on the eraser if I press down on the eraser like so? I dramatically increase it. So if I increase the normal force then acting on the eraser by pressing it down in this manner, I then, therefore, and it turns out in a directly proportional way, increase the amount of friction as well. Basically all that I'm doing is I'm taking the two surfaces and I'm mushing them together. So if I mush the surfaces together, what's going to happen to the friction? It's obviously going to go up. And it's also obvious if I just simply do this. Like so. So notice that the force of kinetic friction acting on the eraser in that case is a lot more than it was earlier when the normal force was a relatively small number. It turns out that the two quantities are directly proportional to each other. It is specifically with this statement that we now quantify the force of kinetic friction. The force of kinetic friction, labeled as F sub k, is directly proportional to the normal force. Now remember that when two quantities are proportional to each other, that means that there is some number, a coefficient, that turns it into an equal sign. That coefficient is written in the following way. The number that appears here in this empirical property of kinetic friction is called the coefficient of kinetic friction. It's labeled by using the Greek letter mu. Okay, this is the Greek letter mu, and with a little subscript k, this refers to what is called the coefficient of kinetic friction. We then pronounce this very simply as mu sub k. The coefficient of kinetic friction is not a property of the eraser. It's not a property of the desk. It's a property of the two surfaces when they're in contact with one another. And it is an empirical property of the two surfaces. Once again, there's that word empirical, which means that it's something that is only measured. As we'll see, measuring it is actually really easy to do. Now, in theory, we should be able to use, for example, the atomic physics that goes on here at the atomic level between the atoms that make up the eraser and the atoms that make up the desk to derive the coefficient of kinetic friction for these two surfaces. But in practice, that's like trying to predict the weather months in advance. There's just simply too many variables. So it's only something that is measured. It's an empirical property. It turns out that measuring it is really easy to do. We'll do an laboratory exercise, for example, a little bit later on. Okay, but for now, a couple of things to say about the number itself. For most common surfaces, like a floor, the desks, wood, etc., usually the number itself is pretty small. Usually the coefficient of kinetic friction is less than 1. There are some materials, however, such as soft rubber, where the coefficient of kinetic friction when you place it in contact with, say, concrete, is actually a pretty big number. In the case of soft rubber in contact with concrete, it's over 2. That's a gigantic number when we're talking about the coefficient of kinetic friction for situations, very simply, that we see around us. For the most part, it's a number that is less than 1. Okay, the number itself is dimensionless. It has no units. And we can actually see that from this empirical description of the force of kinetic friction. Think of it this way. We have here on the left-hand side force in newtons, and on the right-hand side, the normal force is also a force in newtons. So if this is newtons and this is newtons, then this number here has no units. It's a dimensionless quantity. Okay, now it kind of looks like that this right here just sort of pops out of nowhere. But it turns out that measuring the coefficient of kinetic friction, as difficult as it may be to derive, measuring it, turns out, is actually really easy. So let's take a look at a situation in which we could use, if we wanted to measure the coefficient of kinetic friction. I'm actually, in this manner, going to use the same problem that I opened chapter 4 with, involving a hockey puck sliding across horizontal ice. Now what we're going to do is add a little something to the situation. Now the numbers that I gave this version of the problem are exactly the same as how we saw it last time in class at the beginning of lecture, essentially the beginning of chapter 4. And now we're basically going to go one step further. We're going to use the data in this problem. And yes, that's how you want to think of it in this case. We're going to use the data in this problem to actually then calculate the coefficient of kinetic friction. As we'll see, it's easy to do. Okay, now from last time, remember how this problem went. Initially, it's identical. If you recall, we did a little bit of kinematics here at the beginning to find the acceleration. We did the following. We have the puck here starting at our origin. Initially moves to the right-hand side with a speed of v0 at 5 meters per second. Ends up at rest over here after undergoing a displacement x of 10 meters. Okay, once again, think of this here as data. And then we use the third kinematics equation here to find the acceleration. Okay, briefly, we started at the origin. The object ends up at rest. So our expression becomes the following, like so. We did a little bit of algebra to find the acceleration A. After I did those couple of steps, I ended up with this expression here. And then, as I said, the numbers in this version of the problem are exactly the same as how we saw it last time. Plug the numbers in. You end up with, if I remember correctly, negative 1.25 meters per second squared. So, of course, the acceleration being negative here from the kinematics means that it's to the left, exactly as we saw it last time. And then we set up our force diagram, started to look at the dynamics here, and now we're going to kind of zero in on the details of kinetic friction. Okay, first of all, we have here in this horizontal situation, the normal force and mg cancel each other out in the vertical direction, and of course we have this little formula. Now in the problems that I did last time in class, and also for that matter the one that I did at the beginning of class this time today, I wrote down these little expressions for the normal force, but they never factored into any of the problems afterwards. Now it does. The reason why the normal force is important now is because the force of kinetic friction acting upon the hockey puck in this problem does depend upon the normal force. We need to know what the normal force is equal to in order to come up with that description. Okay, now, as the object slides to the right, opposing that motion then therefore is the force of kinetic friction, F sub k now, acting to the left. And like we saw last time in class, it is the force of kinetic friction, of course, that gives us the acceleration. So once again, the force of kinetic friction opposes the motion, and not necessarily that of the acceleration. In this case, they're in the same direction. And now I just add everything up here horizontally by using F equals ma, and we have the force of kinetic friction equals mass times acceleration. Now when I did this problem last time in class, this was basically it. We calculated the net force, which is equal to the force of kinetic friction, and we got our answer in terms of newtons, and then we went on to our next problem. And now we go one step further. We want to write, or find rather, the coefficient of kinetic friction. It is specifically at this step right here that I now write the force of kinetic friction as its coefficient multiplied by the normal force. So this is that last property of kinetic friction. We write it in terms of this little empirical expression. This is where the normal force now becomes important. I need to know what it is in order to find the coefficient of kinetic friction. So I plug in here for the normal force the object's weight. Like so. And notice now that the mass of the object cancels out. So somewhat counterintuitively, the coefficient of kinetic friction actually has nothing to do with the mass of the eraser itself. The reason for this is because ultimately the coefficient of kinetic friction is coming from the following. How these atoms here interact with these atoms. It's coming from that fundamental physics, which has nothing to do with the mass of the eraser itself. It cancels from the expression. And then lastly here, to get the coefficient, just divide by g on both sides. Like so. And because all that I end up with here is a ratio of accelerations, there are no units associated with this quantity, and now I can just go ahead and directly calculate it. So it's nothing more than just 1.25 meters per second squared in the numerator divided by 9.8 meters per second squared in the denominator, and that then gives us the following. Usually we'll see the coefficient, by the way, in examples going out 2 decimal spaces. In this case, it's 0.13. So this is not quite what we're going to do when we eventually do a mini lab exercise on friction, but this is just one version of a situation where you can easily measure the coefficient of kinetic friction. All that you have to do is take the eraser, let it go at some initial speed, measure how far it travels, boom, do a little bit of kinematics to get the acceleration, and then the acceleration divided by g is equal to the coefficient of kinetic friction. It's literally that easy to measure. This is one version of how you can do that. Okay? Okay, next, and to finish with today. Last time in class, we did our basic air track problem in the frictionless case. And yes, next time in class on Friday, it will become our laboratory exercise. But if you introduce friction into that problem, then the situation physically becomes a lot more complicated. Let's look at it in the following way. There are 2 parts to the problem, but for today, we're just going to take a look at part A. That will be good enough for today. Now, once again, just to be consistent here, I kept the numbers exactly the same as we did in the frictionless case last time in class. But now notice that we add a coefficient of kinetic friction between the air track cart and the air track itself. Marco, you all finished?
Yeah.
Okay, you can just bring everything up here, that's fine. Thanks. Oh, yeah, the passage. It should be filled out to one page. Okay, now just to be consistent as I can, I gave the numbers here the same values as we originally saw in this problem, and now we do have a coefficient of kinetic friction. And it says, after I draw it out, that the system is initially moving to the right. So to picture it, once again, here's our air track like so. Here's M1, still equal to a kilogram like it was in the previous version of this example, but now underneath here, there's a coefficient of kinetic friction. Then we still have our string, by the way, draped over a frictionless pulley. The pulley is still frictionless because if it wasn't, the pulley would rotate. We would have to take that into account. We're not doing so. And then here's our M2, once again, as a kilogram. Now in part A of this example, and that's all that we're going to do here today, we're given the following. We're given that the objects are already moving like this when we examine the problem. So something got them moving already in this direction. Whatever that was, we don't really care so much about. It's just that now we want to find the acceleration. But just qualitatively for a moment, think about what could happen. For example, even with friction, is it possible for the objects to be initially moving like this, yet speeding up as they do? Yes, and by the way, that is, of course, exactly what happens in the demonstration from last time in class, because remember, there is no such thing as a frictionless surface. There is a little bit of kinetic friction that is present. However, also think of it the following way. If the friction is large enough, is it possible for the objects to be initially moving like this, yet doing so at constant speed? Is that physically possible if the friction is large enough?
Yes.
Yeah, it is. If the friction is large enough, is it physically possible for the objects to be initially moving like this, yet slowing down?
Yeah, yes.
Yeah, that's possible as well. So I should see all possibilities come out as I begin to set up my equations. So now let's see what happens. Okay, first of all, for M1. Like last time in class with the frictionless case, we still have the following three forces. Normal force N1, the weight M1G, still canceling each other out. Okay, we still have tension to the right-hand side. But now, opposing the motion, we have the force of kinetic friction acting to the left-hand side, like so. And now just from the force diagram alone, you can actually see all three possibilities. That is, if the tension, for example, is bigger than the force of kinetic friction, then the object would accelerate to the right. If the tension was equal to the force of kinetic friction, then the acceleration could be zero. If the tension was less than the force of kinetic friction, then the acceleration would be to the left, and the objects would be slowing down. So just from the force diagram alone, we see all the possibilities occur. Okay, now, the friction here, by the way, is pretty small. This mass is pretty heavy compared to this one as well. So then therefore, I'm just going to intuitively guess that the objects will in fact speed up in their direction of motion. I'm going to guess that the acceleration looks like this. Now, based upon that guess, here's then what happens horizontally. We'll have tension T, positive in the same direction as A, and then minus the force of kinetic friction in the opposite direction. So I add up like so, and end up with an additional force term here in my equation that wasn't present last time in class when I did the frictionless case. Yeah. Excuse me, go ahead.
Why would you guess that the acceleration would be
It's just a guess on my part.
But aren't the weights even, so
They are. So then therefore, because the weights are the same, let's be a little bit more technical, let's say the masses are the same. Because the masses are the same here, and the friction here is pretty small, it's gonna pretty obviously accelerate like that. I don't know that for certain, I'm gonna have to calculate it, but that's just my intuitive guess. Okay, now, before you get to M2, however, you carry this term out as far as you can go. That is, we now write this right here as coefficient times normal force, like so, and then once again, here's why the normal force is important. We need to know what it is. It's equal to the object's weight. So we plug that into the expression as well, thereby obtaining the following like so. So now with the addition of friction here in the equation, you carry it out essentially as far as you can go prior to taking a look at M2. Okay, as is always the case in these pulley problems and blah, 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 you have the two unknowns, tension between the objects, which we don't care, and the acceleration A. So now I take a look at M2. And when I take a look at M2, keep in mind that M2 is not against a surface or anything like that, so there's no friction. M2's force diagram is exactly the same as we saw it last time in class. Once again, we're assuming it's acceleration. Up there in green, we're assuming that the acceleration looks like this. So when I add up the forces here for M2, it's exactly the same equation as we saw it last time in class. It's M2G minus T is equal to M2A. So then here's my second of two equations and two unknowns. And then at this point, we just run through the remainder of the algebra. So then algebraically, I'll jump back up to the top board here for just a moment, and I'll solve for tension T. So I'll move this friction term to the other side, like so. And then take that expression for the tension and plug it into here. Once again, just be careful about your algebra. Make sure you distribute the negative sign through both terms. So I now have M2G minus T. So minus that guy, minus the first term, minus the second, equals then the right-hand side of my expression here, the M2A. And once again, I now just have one unknown, which is the acceleration. So for the remainder of the algebra, what you do is you take this term here, move it to the other side, and when I do, I'll factor out the acceleration for each term. So once you get the hang of doing this for a couple of problems, you can start to combine some of these minor algebraic steps together like so. And then lastly, just divide by the parentheses on both sides to obtain our acceleration A, and that then gives us the following. And then before we plug in the numbers here, let's just examine the expression itself to see what can physically happen. Notice in the numerator of the equation that basically three things can happen. If this number here is greater than this number, then the acceleration would be positive. It would be exactly as I guessed, which would then therefore mean that the objects speed up in their direction of motion. If the friction is large enough, however, if the numbers work out, it's possible that these two terms here are equal to each other, and then therefore the acceleration would be zero, and then therefore the objects would move at constant speed like so. If the friction is large enough, it's possible for this number here to be bigger than this one, and then therefore the acceleration would be a negative number, meaning that it's opposite of what I had guessed up on the top board. If the acceleration is opposite of what I had guessed up on the top board, as the objects initially move like this, they would be slowing down as they do. And then lastly, before I actually plug the numbers in themselves, notice what happens in the frictionless case. In the frictionless case, this term is gone, and there's the acceleration that I derived for the frictionless air traffic problem last time in class. And then lastly, let's just plug in. Now it is going to be a positive number here, by the way. The friction's not all that much in this problem. So I have 1 times 9.8 for the first term, 9.2 times 1 times 9.8 for the second term, divided by a total of 2 kilograms, and you end up with, yes, a positive number of 3.9 meters per second squared. So it does speed up in its direction of motion in this problem. So notice that, just to finish, with the introduction of friction into situations, then the situations can become physically more complicated. Any questions? Okay, very good. Chandler, is good enough.